Okay, I guess we can get started. So as I mentioned, so last time we discussed all the ergodic theorems, and we saw the proof of the subadditive ergodic theorem. So now the next tool from probability that we actually need to discuss random walks is martingale. So first of all, we have to define a conditional expectation, which you might have studied in your measure theory or probability course already. So, but let's recall that. So, in general, what is the notion of probability conditional expectation? So we have a space X. And we have a two sigma algebra. So we have A, so X A mu is usual probability space. But then we can consider B in A is a sub-sigma algebra. So meaning that of all measurable sets, we just consider some of them. Okay. And now we can easily we can look at L1 of X with respect to B. So these are the functions that are measurable with respect to B, so such that the pre-images of Borel sets are in B. This is a subset, is a subspace of L1 X with respect to A. So at first, this seems very abstract, and in fact, the definition is very abstract. But this actually happens in probability quite a bit. Usually, whenever you have a process, you can define some sigma algebra, which tells you that when you're considering only some outcomes of your random stochastic process, and then when you consider more outcomes, you have a bigger sigma algebra. So this is actually what happens. We will see more in detail. Okay, so now let's define the conditional expectation. So given f in L1 of XA, we want to produce a function in this smaller space. So the conditional expectation and this is a function which we call it as E of f given A. And this is the only function that satisfies the following property: is the unique element. So this is a function of L1 X B mu, such that so it's a unique function. It's in the smaller space, and it has two properties. Okay, so first one, as I said already, so unique element, call it G. Okay, so again, G is in L1 of X B mu. And the second is, so it is measurable with respect to the smaller sigma algebra. And the second part is that the average stays the same in the following way, that if you take the integral of f d mu on every B is the same as the integral of G d mu in B for every B in the smaller algebra. So so basically you have a function that is measurable, so that you see the pre-image of Borel sets lies in this wild algebra. There are strange, possibly complicated sets. And then we want to make a function that is measurable with respect to the smaller algebra, meaning that the pre-images are better behaved. And so the idea is you kind of project once again. So you find a new element in this space, that is measurable with respect to the smaller sigma algebra. And also, whenever you take a test set which is in the smaller algebra, the average is the same. Okay? So this is the statement. And so, well, the existence of this is not really that easy to show, but we will take this for granted, the existence. And so what are the properties? So the proposition about properties of conditional expectations. So what are the properties? So first of all, this is linear. So first of all is for every lambda, some scalar in say R, and for every f and g in L1 of XA, yeah, I drew it like this, then, well, the conditional expectation of f plus lambda g given A is indeed linear, is conditional expectation of f plus lambda conditional expectation of g. So this is not so surprising. The other thing is if f is B measurable already, well, what is the conditional expectation of f? Oh, sorry, this is B. Yeah. We take the expectation with respect to, oh, B here as well, sorry. Yeah. So we take, what is the expectation of f conditional on B? Well, what do we want to do? We want to find a function that is B measurable, and it has the same integral as f on every B set. Well, if f is already B measurable, then you just take f itself already works, right? So this is kind of, so far is a bit dry, but we'll see what else. So the second thing is if f is independent of the random variables of x1, xn, random variables, so you take any random variables defined on the same space, well, what is the expectation, the conditional expectation of f given the sigma algebra generated by x1, xn? So what is the sigma algebra generated by x1 and xn? Well, this is the smallest sigma algebra for which x1 and xn are measurable. So such that, so that it contains all the preimages of Borel sets by this. And so this is literally just the expectation of f. So it's a number. Because, yeah. So this is because they are independent events. So in some sense, having, you know, the information that you know the outcome of x1, xn is irrelevant. So your best guess of the expectation of f is just the integral of f. So we will see examples of this because, yeah, this is a bit formal, but actually it's a very important notion in probability. It has a lot of usefulness. So maybe are there any questions about the definition? Yeah.
When we have the existence, that's given any subalgebra?
Yeah, that's right. That's right. So every given two pairs of sigma algebra, so this exists. Okay, so now let's see maybe some examples. So let's see. Yeah, by the way, we can also add the remark. What is the sigma algebra generated by x1, xn? So given x1, xn, sigma of x1 xn is the smallest sigma algebra that makes each xi measurable, meaning what? Meaning that sigma of x1 xn is the sigma algebra generated by xi inverse of a Borel set, so B, right? Such that I is in 1n and B is in a Borel sigma algebra of R. So yeah, so again, this seems very abstract, but actually in probability, this comes really natural when you have a sequence of random events. So let me start. So let's see examples. Okay, so here's an example. So suppose you have xn random variables, and each xn from your space x or omega, or let's call it maybe omega, to 0, 1. So for instance, classic coin toss. So suppose that these xn's that you're looking at are draws of some random variable. So what does it mean to condition on sigma 1, sigma xn? Yes, it basically means that you can assume what is the outcome of these variables, because you see what are the measurable sets here, where the measurable sets in this sigma algebra is like you decide is the preimage of 1 or 0. So it's either the set where the outcome is 1 or the set where the outcome is 0, right? So maybe we can say that the sigma algebra generated by x1 xn is, you see, is the set of, every set is of the form, right? So x1 equals a1, a xn equals an. So this is where, right, such that, so yeah, such that a1, an are in 0, 1 to the n. So certainly contains all those sets, and basically these are all the sets. Like yeah, okay, maybe yeah, just any. In fact, you can select not just, yeah, you can even select only 1 or 2 outcomes, and it's this is one measurable set in this sigma algebra. So yeah, so this is definitely, yeah, this is essentially it's almost, yeah, it's exactly almost the same. Maybe we can even say for a subset. So x1 xa1, and yeah, if you want to be precise, you want to say there's a subset, right? So xi1 equals a1, xir equal ar, so some ar 0 r plus n. So you can yeah, prescribe the outcome of whatever r out of this n variables. Okay, and now what happens when you do the conditional expectation, right? So let's compute the following. So what is f, expectation of f, given sigma of x1? So f is a function. And now I do this first coin toss. And I want to condition on the first coin toss. So what do I do? So there's 2 options. So either either the first coin toss is 0 or 1, right? And if the first coin toss is 0, well, I take the average of f given the fact that the first coin toss is 0, and then I take the average of f given the fact that the first coin toss is 1. So here's what we get is so we define C0 as x1 inverse of 0 and C1 as x1 inverse of 1. And so here we get the characteristic function of C0 times the average of f. We call it mu or p, let's say mu, right, over mu of C0 over C0 plus 1 of C1 f C1 d mu over of C1. So you see, this is a function. It's still a function, but it's a much coarser function. So f could depend on many, many things. So if we just don't condition at all, we're just taking the expectation of f. This is a number. Now, here we're conditioning on the first outcome. So it's still a variable, but it's a much simpler variable. It's a variable that has two values. If the first digit is 0, you're taking the average of f on the set where the first digit is 0. And if the first digit is 1, you take the average of f on the space where the first digit is 1. So this function, now it's measurable with respect to the much smaller sigma algebra, which is this one. Okay? So, okay, now when we have, maybe we can look at really some exercise about this. And also for notation, sometimes we also just write the expectation of f given x1, xn. Well, this is just the same as the expectation of f given the sigma algebra. Same thing. Okay? So now, yeah, so now let's look at an exercise, for instance. So let's say again that we are doing a coin toss. So xn are just 0, 1 random variables. They are IID, and the probability of xn equals 0 is 1/2. Suppose you do the usual coin toss. Okay. So now, and you define Sn as the sum of the first n variables. So what's the conditional expectation of S100 given that x1 equals x2 equals 1 and x3 equals 0? So suppose I tell you already what is the outcome of the first three variables, right? So you see, because if you just condition on x1, x2, and x3, you're gonna get a function which depends on the outcome of the first three. So now I even just give you what is the outcome. So now this becomes a constant. So what is the constant? Again? 49.5, something like that. So something like that, right? Because what? Well, because what is this? This is right. So this is the expectation of, well, x1 plus x2 plus x3 plus everything else from 4 plus to 100, right? Given, so this is bilinear, this is, well, literally the definition. And then and then what? Well, you see, we know the expectation of x1 plus x2 plus x3 given these guys. Plus the rest of the sum. Let's see why is that the case. Well, so because you see now this function, this function is already measurable with respect to the sigma algebra, so we can tell its value. And so what is its value? Well, it's gonna be 2, right? 2. And what about this guy? Well, here in this case where this is independent of that. So since they're independent, the fact that I have this information is completely irrelevant. Your best bet is to just take the average of this. And so what's the average of that? Well, it's 1/2 times 9 times the number of trials. So this is 1/2 times what? 97? Yeah, so that's what it is. Yes. So this is what is it 50.5? Yeah. Okay. So this is an exercise to remember what is the conditional expectation. And now, why do we care about conditional expectations? Because indeed, to define martingales, the definition of martingales is given in terms of conditional expectations. Okay, so by the way, another type of conditional expectation that we really want to look at is the expectation with respect to the invariant sigma algebra. So once again, so if you have, x a mu t, a measure preserving system, okay. And so you can define the invariant sigma algebra, the invariant sigma algebra as, and we call it AT. Well, these are all the sets in your sigma algebra that are invariant under, in fact, up to measure 0. Okay. So here's a question. What are the functions that are measurable with respect to this sigma algebra? So note that f is AT measurable. So you see, this measurability seems like a very abstract concept, and it kind of is. But it has interesting interpretation. So what is a function that is immeasurable with respect to the invariant sigma algebra? Well, this means that for every C in R, if you look at the set of X such that f of X is bigger than C, this has to be in the invariant algebra, right? So what does it mean? It means that this has to be equal to its preimage. So this has to be equal to what? To its preimage. So what is the preimage? Is the preimage is the set of X such that f of t x is bigger than C. So what can we conclude from this? So you see, you have a function such that the sublevel sets or superlevel sets are invariant under T for every level. So f has to be invariant, right? So this, as a corollary, this shows that f composed with p has to be equal f almost surely. So you see, there is this notion of measurable first for this sigma algebra, and this captures something very dynamic, like invariant functions. So this is kind of neat. So this, in dynamical context, this is a really, really important sigma algebra. And in fact, maybe you can start guessing what happens. So the proposition is like this. So what is the conditional expectation with respect to the invariant sigma algebra? Right. So again, so you start with x a mu p, a measure preserving system. Then for any f in L1, well, what is the expectation of f conditional on the invariant sigma algebra? It's an invariant function that has the same averages as f. So what is it? What? Well, half is not invariant. Yeah, f is anything to start with, right? So f is not invariant. But as you said, like, so this is what we called before f bar, which is the limit as n goes to infinity of the Birkhoff average. So you see, we see once again this ergodic theorem coming up in this interpretation, that you see we also saw that the operation f bar is a projection from the set of from measurable functions to invariant functions. And it's also projection in the following sense, that it's the conditional expectation of f with respect to the invariant sigma. So everything kind of checks out, which I think is a beautiful thing. Okay, so now, yeah, so okay, we can prove this. So we need to check by the existence and uniqueness that f bar satisfies these properties. So first of all, we have to check that f bar is in L1 x at. Well, this we know by Birkhoff's theorem, right? So this is by Birkhoff's theorem. We already proved that. And now the other thing that we have to show is that for every b in AT, so for every invariant b, the integral of f bar d mu equals the integral of f d mu. Okay. Okay, so for that it takes just a little bit. It's not too complicated. So first of all, so we can consider the usual splitting in f is f plus minus f minus, taking the positive and negative part. So what is f plus? Well, f plus is the max of 0 and f minus, right? Well, it's the negative part. Well, we can define it just by difference, but this will be negative. So f minus would be f plus minus f, and this is always negative. So by doing this, the composition, we can assume that f is positive. Like we do it first for f plus, and we do it with f minus. Okay, so assume f is positive. And so now what we do is the following. So the integral of f bar d mu over b, well, this is the integral of 1 over the limit of 1 over sum of f composed with ti, I equals 0 to n minus 1 d mu. So this is the integral of the limit. And how do we compare it to the limit of the integral? Are they the same? So here we have the limit of the integral. So how do we compare the integral of the limit with the limit of the integral? What is the classical lemma? Pareto's lemma, and in fact, it requires that f is positive, so that's why. And so the integral of the limit, it would be, is less or equal than the limit of the integral. Okay, very good. And now here we're in good shape because b is invariant and t is measure preserving, right? Okay, we use dominated convergence. The issue is, how do you dominate this? Right? So point was, so okay, maybe you can use dominated convergence, but I don't see how it's trivial, because you see, each f is in L1, but f composed with T, you know, the max of f could be in various places where you when you compose with T. So it's not completely trivial. Maybe there is a version of using it. Okay, so but anyways, so here we are good to go because each of those is just the integral of f. And you take in the average, so this is just the integral over b of f d mu. So this gives 1/2 of the inequality. So now let's look at the other half. So the other half is by truncation. So we let Fn, the minimum between f and n. So n is some number to truncate. And since f is in L1, then, yeah, so then there exists, so for every epsilon, there exists n, such that the integral of Fn, basically the integral of f is not bigger over the whole space, is almost the same as the integral of the truncation, right? Because the total integral is fine. So we can truncate such that this integral is a bit smaller, but really not much smaller. Okay, and then we apply dominated convergence because this is bounded. So by dominated convergence, the integral of Fn d mu b is the limit as n goes to infinity of 1 over n. The integral of Fn composed dti d mu. Right, this is right, this is not even dominated convergence. This is just writing out the invariance, but then by dominated convergence, we can flip the limit with the integral. And okay, this is less than the integral of f. Yeah, so we can replace this by f. like that. And this one, yeah, this should be the integral of f bar, right? By definition. So this is the integral of b of f bar d mu. So the integral of fn is less or equal than the integral of f bar. And the integral of f is less or equal than integral of fn plus epsilon. And so we're done, right? So from here, we get that the integral of f d mu is less or equal than the integral of f bar d mu plus epsilon. So yeah, so not only, you see, in the classical ergodic theorem, we say that f and f bar have the same average, which is true. But it's also true that they have the same average on each invariant set, which again, if the system is ergodic, which is how you usually apply it, it doesn't make a difference because the only invariant sets is either full measure or measure zero. But if there are other invariant sets, it's still true that the average of the Birkhoff average on an invariant set is the same as the average of the original function. So far, so. Are there any questions, comments? Okay, very good. So, okay, so now we are ready to give a definition of martingale. And we can state the martingale convergence theorem. Okay, so and yeah, so we already noticed that if you take f in L2, then this is the orthogonal projection. So the same remark, we already noticed that if f is in L2, then the expectation of f with respect to AT is the orthogonal projection of f onto L2 invariant. Yeah, this is already. Okay, so now we can define martingales. So what is the idea of a martingale? Well, the idea of a martingale is that the martingale is the outcome of a fair game. So let me write that. And here, the fairness of it is the important point. So here's an example. I play with someone, with coin tosses, for instance. And at some point, so if it's heads, I win $1. If I tail, I lose $1. Right? And now, at some point, I'm playing, and after 10 rounds, I'm up 100. No, 100. You can't. I'm up $7. Okay. So now you see this scene. You see that after 10 rounds, Giulio is up for $7. Now you go away, and okay, and you know that they played another 20 rounds. So now if you want to guess, what would be the best, what's your best guess of the wealth of Giulio after 100 rounds? He was winning of $7 after 10 rounds. What's your best guess after 100 rounds? 7? Anyone else has more? Is that different? Yes? Exactly. So this is, if this is really like usual coin toss, your best guess should still be 7. Of course, if you didn't know anything about the game, your best guess would be 0. But given that you already know the outcome of the first 7, then it's easy to, I mean, it's not easy because in this case, the variance would be very large for other, up to 100 steps. But still, that's the best guess. That's the expected value, right? Yeah, it's like if I ask you to, estimate the richness, the wealth of an average American, and then, okay, maybe you could say at 50, and maybe you say, okay, it's I don't know, $200,000. But then if you find out this guy's Elon Musk, and at 49, he has $200 billion, and I guess, oh, how much will it be when it's 50? Well, it could be a billion, 99 billion or something. It's not going to be 200K. Okay? So that's the point of conditional expectation. So the definition is the following. So a sequence xn of random variables is a martingale if the expectation of xn plus 1, given that you know all the history, x1 up to xn. So I know what happened until yesterday. What's your best guess for your average wealth today? If you know the history until yesterday, well, your best guess is that you were still going to be as rich as yesterday, just xn. Okay? So this is still a random variable because it depends very much on your past. But for the future, well, you don't have any better guess. Of course, things could go better or worse for you, but that's your guess. Okay, and clearly you have a notion of super martingale and sub martingale if you have inequality. So it is a sub martingale. Yeah, so this is a pessimistic notation. Your American dream is dead. A super martingale is if you're gonna, on average, you expect to get richer tomorrow. Okay, so what is an example of martingale? We kind of said it, for instance, whenever you have IIDs random variables with average 0, then that would be a martingale. So example, if xn are IID with expectation of each of them 0, then the new martingale yn, which is x1 plus xn, is a martingale. Because clearly you can, if they're independent, once you condition on x1 xn, well, it doesn't matter. Yeah, you don't what xn plus 1 doesn't matter, right? So you can do e of yn plus 1 given y1 yn, given y1 yn is the same as given x1 xn. So this is the expectation of xn plus 1 plus xn plus x1 given x1 xn. So these cards are already on the table. There's no guessing involved. So you just have to guess the next one. But the next one on average is going to give you 0. So this is x1 plus xn. These are already collapsed to a natural number. You don't have to do any average anymore. And you have xn plus 1 given the previous ones, but it doesn't matter because this is independent of the previous ones. So this is just the of course, if the expectation was positive, then this would be a super martingale. If the expectation is negative, this would be submartingale. Yeah. So this is x1. So that's why random walks and martingales are really, really close to each other. Okay. So okay, so now basically we can give the statement of the martingale convergence theorem, which, as I said, in a way, is the last ergodic theorem that we're going to discuss, because it's not quite in the same setting as ergodic theorems, but it has lots of similarities. It's telling you that certain average exists as time goes to infinity. So okay, so here's so if you have xn, everything is in L1 of omega, respect to measure mu, be a submartingale. And you want also some integrability condition. And it's it has to be for it. There are many variations, but for instance, it would be enough for us to say that the supremum of the expectation of xn plus, so the positive part of xn, is uniformly bounded. So for every n, this integral is always bounded by the same constant. Then there exists some random variable x infinity from omega to r, such that the martingale converges, again, almost surely, such that xn converges to x infinity almost surely. So you see, the submartingale condition is very similar to the subadditivity condition that we had in Kingdom, right? And I think you can formally pass from one to the other. They're not equivalent, but in certain cases you can apply either. I mean, your xn is basically this co-cycle, and so very similar. Sorry?
Oh, is the subadditive co-cycle going to be the sum of?
No. This xn is each of them. So for in our statement, what we had for the subadditive cocycle was an divided by n. So that's the this would be the right parallel. But I don't think they imply each other. But I think in several situations you could maybe apply one or the other. Yes.
So I remember like the definition of submartingales, like the expectation is like should be greater than x, so like less than x. Expectation of x plus 1 given x martingales.
Right.
Greater.
Well, either way, the theorem works in both in both for submartingales and supermartingales. So it's a matter of definition. So this makes sense to me that this would be the definition, but maybe some other people use the other convention. Yeah. So, well, I can double check what is the most common convention, but yeah. Okay, so yeah, so of course, basically the same is true for super martingales, except instead of plus, you want the negative part to be integrable. Because you see, I mean, some martingale has this property that the xn plus 1 is less than the xn. So if you always want an upper bound. So once you have an upper bound, you get another upper bound for the next term and so forth. Like, yeah. Okay, so okay, so here's an example. Now let's finish maybe with this other example, which is kind of neat. It's not the usual one. It's like this. So you start with a sequence xn of IID variables with the following distribution. The probability of xn equals 0 is the same as the probability of xn being 2, which is 1/2. So this variable is either 0 or 2. Okay, and then the question is this. Then if you consider yn, not the sum, but the product of this is a martingale. It's kind of neat because it's multiplicative, but it still is a martingale. Let's try, right? So E of yn plus 1 given y1 yn. So yeah, what happens, right? So you know everything, and the nth plus 1 is the multiplication of yn times xn plus 1. So this is the expectation of xn plus 1 times yn given, for instance, given yn. But now yn and xn plus 1 are independent. So you can take out the yn. So this is yn times the expectation of xn plus 1. And so what's the expectation of xn plus 1 is 1, because it's 0 or 2 with probably the 1/2. So this is yn. Now, is this martingale integrable? Let's see, is it integrable, right? So, so we want to compute the expectation of yn. Well, if you think about it, it's a product of zeros and twos. So the only way that this one is non-zero is if all the outcomes are 2. Right? So this happens. So this is 2 to the n with probability 1/2 to the n. That's the only outcome. Otherwise, everything else is 0. So this clearly is 1. So this is integrable. And so it is, so indeed, there is yn converges to y infinity almost surely. Yeah, the question here is that does it also converge in L1? Here's the nexus. does yn converge to y infinity in L1? This is up to you to remember. So in a ergodic theorem, we have convergence almost surely in L1. Here we have convergence almost surely. But the integral is always 1, right? So if it has convergence in L1, then y infinity has to have integral 1. But what do you think y infinity? Yeah, it's gonna be 0. So I don't think it. So I don't think you have convergence. Okay, anyways, this is to think about it. Okay, I think I'm done. So I guess, yeah, I'll see you next Tuesday. Yeah.